Hey, I'm walking here. Hello, and welcome to our presentation on socioeconomic factors, seeing if they're predictors of per capita income in Chicago. This presentation is presented by myself, Christian Longo, Ethan Rue, and Bryce Whitney. The goal of this project is to utilize 5 other variables to predict percent income in the Chicago area. Our goal is to be able to use this model in other urban areas or in turn generalize it to other areas that are similar. Our data set, which involves 78 communities within the Chicago area, taken from the years of 2008 to 2012, we utilize 6 variables. The first variable, our dependent variable, is per capita income. The 5 independent variables we are using to get our model to predict per capita income are as the following: the crowded house percentage, percent of households below the federal poverty line, the unemployment rate, the percent without a high school diploma who are above the age of 25, and finally, the percent who are considered a dependent. A dependent is someone who has the quantity years of age that are outside the range of 18 to 64. All right, another slide. All right, so what was our data intended for? So the data set itself utilizes 7 variables, while we only utilize 6. The 7th variable is known as the hardship index. The hardship index is rated on a scale from 0 to 100, with 100 representing the most hardship. We first originally were going to utilize the 6 variables to predict hardship index, but upon further research, we found out that hardship index is directly calculated from the 6 variables I previously discussed. So with this, we have decided to utilize that dependent variable of per capita income, and then we're going to attempt to predict it using models of the other 5, which in our case are independent variables. So how will we utilize our data? So in general, we are looking to find correlation between these variables. To improve on these correlations, we're utilizing a stepwise regression, which in turn will knock out variables that aren't indeed deemed fit to stay within the model. So first, we're starting with a first order model, and we are going to use stepwise regression to eliminate variables that don't need to be there. They're not helping our case. Then with that reduced first order model, we are going to implement quadratic x's, so x squared, and interaction terms in a second order model to see if we can improve on our data and our model even further.
Hi, I'm Ethan, and welcome to the Chicago Bean. So let's begin by looking at a correlation matrix of the variables of our data set. So we can see some positive correlations between our dependent variables, and we also note a significant negative correlation between all of our dependent variables and our independent variable per capita income. Cool. So now let's look at our complete first order model. So here's a complete first order model with the 5 socioeconomic indicators modeling per capita income of a community in Chicago. So from here, we see a statistically useful model for predicting per capita income of communities. This model has a very small p-value and an adjusted r-squared of 0.77. So all independent variables are negatively correlated with per capita income for this model. So based off the correlation matrix, this is what we would expect what would happen. So now to improve our complete first order model, we use a stepwise regression model to see if we could drop any of our independent variables. From the stepwise regression, we find that we should only include the variables percents of dependents, so that's under 18 or over 64, percent without a high school diploma, and unemployment percentage. So this model tells us to drop the crowded housing percentage and percent below the federal poverty line. So including just these 3 variables gives us the smallest AIC value of 1,372. From the stepwise regression, we can create this first order parsimonious model. So this model has a slightly higher r-squared value than the complete first order model and a very small p-value. So looking at this model, we can see that the intercept term is 76,041, and all the coefficient terms are negative. So since all the independent variables are positive terms, so it's in terms of percents, all those will be positive. That means that our model will never give a per capita income prediction higher than 76,000, which is the intercept. So our data set primarily had data on lower income communities and is not a useful predictor of higher income communities. So this is fine because our model is only going to be used for low income, like urban areas. Okay, so looking at the residuals, so the histogram of the residual shows us that our variances are normally distributed because of the symmetric bell shape of this distribution. This histogram is centered around 0, which indicated that our normality assumption is likely to be true. So we do have one data point that is a large outlier, and this is because our data set includes data on the near north side, a wealthy community with a per capita income of 88,000. So as I said earlier, it's expected that our model will not be accurate for this higher income areas because the highest it will ever predict is 76,000. So that is where this large residual comes from. So this quantile plot also tells us that our dependent variable is normally distributed because it is roughly linear here. And you can see the one outlier I mentioned previously up here. So we can kind of ignore that. And also looking at the VIF values of our 3 independent variables, we can see that there's no evidence of multicollinearity since the VIF values are less than 10.
And we're live from Midway Field. We were definitely happy with our first order model, but we don't think it's the best possible model. We think there's definitely room for improvement. And to look further into it, we checked to see if there are any second order terms that could make our model even better. So we took the 3 terms from our first order model and expanded it out into a complete second order model, giving us 3 first order terms, 3 interaction terms, and 3 squared terms. And this was an input for stepwise regression. And as you can see on the slide, 6 of these terms were selected. So our new model now consists of the 3 first order terms that we originally had, an interaction term between the percent of people who are under 18 or over 64 interacting with the percent of people who are 25 without a diploma. And then there's 2 squared terms, which is the percent of people who are 25 without a diploma squared and the percent of people who are 16 and unemployed squared. And this is now a second order model. And after fitting it on the data, there's a couple key aspects to notice. First, we see the global F-test produces a p-value of 0, which is exactly what we're looking for. It means we have a statistically good model. Then we see the adjusted R squared is about 87%. This is roughly 10% more than our first order model, suggesting that this model might be a better predictor of per capita income as it's able to capture more of its variance from the model itself. And the last aspect we notice is the standard error S has decreased by about $2,000. So it's now roughly $5,000. And this may not be ideal, but gives us a range on estimates of plus or minus $5,000, which, considering per capita income, can be as high as $90,000 in our data set. This will be good enough to give us a pretty good estimate of where the per capita income is likely to fall. So after fit our model, we had to do some residual analysis to check the normality assumption. And both the histogram and the QQ plot suggest that our residuals do generally follow a normal distribution. There's that one point on the far right that throws everything a little bit off, but in general, our residuals follow a normal distribution. And since we know that a little deviance doesn't have a big effect on the model, we think that the normality assumption is a completely fair assumption to make in this case. And finally, we looked at some multicollinearity within our second order model. And this is where the second order model starts to lose some credibility. As you can see, we looked at the variance inflation factor, and 5 of the 6 terms, independent variables, had a VIF over 10, some as high as 70. So this suggests that the second order model has pretty strong multicollinearity within the model. And this is definitely something that you'll want to take into account when deciding which model you want to use for perhaps different purposes or whatever your main goal is. And I'll let Christian touch upon this a little bit more.
So in conclusion, to start, we will look at the first order stepwise reduced model. In terms of multicollinearity, it is lower, so it is more generalizable to areas outside of Chicago. other urban areas in the United States. But the model also has a lower adjusted R-square value, which in turn implies it has less predictive power. In contrast with our stepwise reduced second order model, the multicollinearity is higher, implying it is less generalizable to areas outside of Chicago. However, the large R-squared adjusted value increases its predictive power and shows that this model is better for predicting within Chicago. One final point, if you're looking for a model that has more predictive power, especially for the area of Chicago, you should focus on using our second order stepwise reduced model. However, if you're looking for a more generalizable model, it could be more easy for other data sets, other cities, we recommend using our stepwise reduced first order model.